Okay, so hello everyone. Welcome to our this week Rogers Efficient AI seminar. And today we're very glad to have Professor Nikhil Shukla from the University of Virginia to give us this talk. And Professor Shukla is currently assistant professor at the University of Virginia with a joint appointment in the Department of Electrical and Computer Engineering and Material Science Engineering. He served as the UVA Deputy Site Director of the Multifunctional Integrated System Technology Center. And he received his PhD from the University of Notre Dame. His research interest lies in the general area of the physics of computing, and he's presently interested in exploring opportunities for efficient computing through device circuit and computing model co-design. And he has authored and co-authored over 75 journals and conference papers, including many prestigious journals like the Nature and so on. And he is a member of the IEEE Nanotechnology Council Committee on Quantum, Neuromorphic, and Unconventional Computing. He has served as the session chair and the TPC members in many prestigious computing and the VSI conferences. So now let's welcome Professor Shukla to give us this talk.
Hey, thank you, Bill. Thank you. So first of all, good morning to everybody, and it's a pleasure to be here. So I'd like to take this opportunity to essentially talk about a few of concepts in designing physics-inspired computing platforms for solving a class of problems that are traditionally considered hard to solve on digital platforms even today. And the specific class that I'm going to be discussing is that of combinatorial optimization. So we'll dive straight in. It's incontrovertible that digital computing has really transformed society, and we've seen Moore's law really revolutionize things. But it turns out that if you look at the spectrum of computational problems that are available, it turns out that there is a class of problems, and specifically for today's talk, we'll focus on this idea of combinatorial optimization, which are still considered challenging to solve on digital hardware. And so it turns out that because of the fundamental hardness of the problem itself, there is a need and motivation for exploring alternate computing paradigms to address this class. And so the sort of the most representative example of the combinatorial optimization problem is that of the traveling salesman problem, the one that you see here on the left-hand side, which is that, the easiest way to think about this problem is that given a set of cities, the idea is to calculate a route that visits every city once and only once and gets back to the original city such that the total distance that has been traveled is as small as possible. And so it turns out that this idea such problems are known to be difficult to solve on digital computers. And they belong to this class of complexity class called as NP-hard problems. I also want to just quickly run through a few other examples of such problems, and some of which that we will extensively use in today's talks. So the other one is known as the max cut or the maximum cut problem. And the way to think about this problem is given a graph such as the one shown here, the idea is how do I divide the nodes of this graph into two parts, such that the total number of edges that intersect the cut or this partition that is shown here is as large as possible, or it's maximized. And then the other one is, again, something that is very archetypal and prototypical for combinatorial optimization, is that of Boolean satisfiability. So, the way to think about this problem is given a Boolean expression in this form here, which is known as the conjunctive normal form. The idea is to find an assignment for these variables, x1, x2, and so on and so forth, such that y equals 1. And so it turns out that, this class of problems is traditionally known as combinatorial optimization. And of course, the overall class is very big. Many problems fall into this class. And it turns out that for many of these problems, we still don't know how to solve these problems, or we don't have efficient algorithms in the digital domain to solve these problems very efficiently. So, of course, the other point I want to emphasize here is that this is not beyond just the theoretical curiosity or from a theory standpoint, many of these problems find extensive applications in a wide range of areas, ranging from machine learning, electronic design automation. So if you're thinking about, say, interconnect routing, the most optimal floor plans for the interconnect routing would be a problem that would fall into this class. And similarly, other areas such as power management would also use some version of combinatorial optimization. And so, again, considering the focus here is on AI, one specific example I can give you for where this problem finds an application is, let's say if you're designing a neural network model such as a Boltzmann machine or restricted Boltzmann machine, it turns out that you have to come up with accurate estimates, or you have to model accurately the probability distribution of the input data. And so here, this is the early snapshot of some of the work that we have been doing, where we can now create these physics-inspired models that can be used to estimate the probability distribution that can then be used for training these RBMs or Boltzmann machines, depending on the model that you're using. And so the point I want to really drive home here is that the class of combinatorial optimization problems is wide, and it finds extensive applications. And so, of course, for this talk today, I'll essentially focus on the sort of approaches that we've looked at for solving the overall broader class of problems. And then, of course, the idea being that if we can accelerate this fundamentally, then all of these applications, including AI, stand to benefit from it. So before we get into some of the specifics of what approaches we're going to look at, I want to spend the slide on just explaining and giving you an intuitive feel for really what makes these problems so hard, and why is it that we struggle when it comes to solving these problems efficiently. And so I'll start off with this very simple example of solving the max cut problem again. And so just to remind you, the idea is to divide the nodes of this graph into two parts, such that the number of intersecting edges for the cut is as large as possible. And so if you think about, let's say, a brute force approach of designing the max cut or for this graph, or max cut solver for this graph, one way you could think about doing this is, let's say we can start by listing out all the combinations that could be possible. So in this example that is shown here, you can see that I can place one node on the left-hand side, which will contribute to one of the sets created by the cut, and then the other three nodes are placed on the other side. Similarly, I can do that for another configuration where I pretty much split the graph equally, and I get two nodes on either side of the cut. And so in this case, the cut equals 3, and then I would have to essentially list out all the possible combinations for this specific graph. And it turns out that I can then identify the one which has the maximum cut, and that would be the max cut for this problem. The important point, though, is that for a 4-node graph, I have to evaluate 8 configurations. Now, when I go from a 4 to a 5-node graph, the total number of configurations I would have to evaluate for this would come up to about 16. Right. And so the key point here with these kind of problems is that as the number of nodes increases, the number of configurations that you might have to evaluate can increase exponentially. So in fact, in this case, it would increase with the exponent given by 2 raised to n minus 1. Now, of course, it turns out that not all combinatorial problems are going to require you to estimate all these configurations. There are some for which we have found efficient algorithms, so they're typically known as polynomial time algorithms. But it turns out that there are many other problems, max cut, traveling salesman being classical examples of them, where we still do not know how to solve them efficiently, where for certain cases, we still have to explore the whole phase space. And so it turns out that this is this is really what contributes to the hardness of the problems, if you will. And so to give you an example of how this shows up in sort of real experiments, here what we did was we took a solver that's available on the web that actually allows you to look at computing actual optimal solutions to the problem. And what you realize is that as we go from testing 32 node graphs all the way to 128 node graphs, you can see how the runtime required increases exponentially. And by the time we are at 128 nodes, we have really run out of the maximum time allotted by the solver for solving a problem. And so, if all you can solve is 128 nodes, you can imagine that by the time we get to graphs of practical interest, which are in the thousands or tens of thousands of nodes, such an approach would really be unfeasible, if you will. And so overall, this is really the driving force for exploring alternate methods for solving the class of problems. Of course, the way we manage through this as of today is we essentially use heuristics, where we sort of have to tailor the heuristic specifically for input classes of certain problem that we want to solve. But that also comes with its own limitations, because now the heuristic can be very sensitive to the type of problem you want to solve, the input characteristics of the problem, and so on and so forth. And so while that is sort of a temporary solution, there is an active need for looking at more powerful solvers for these kind of problems. Now, one other property that I'd like to quickly discuss here, which will then set us up for looking at alternate computing models and paradigms for these class of problems, is a property known as, is a fundamental property of these combinatorial problems. So when you try and quantify or mathematically define these problems, what you're really trying to do is you're trying to maximize or minimize a discrete objective function that is used to define this this problem that you want to solve. And so, for example, if you look at the case of the maximum cut problem, what we're really trying to do is we're trying to identify a configuration that maximizes the total number of cuts, or sorry, the total value of the cut. Or if I now turn that around into a cost function, if I add, say, a penalty, then in that case, we're trying to minimize the cost of that function. And so the way to think about these combinatorial optimization problems is really that you're trying to minimize or maximize a discrete objective function, and that is used to define these problems. And so this fundamental property of minimization of an objective function actually finds a very elegant equivalence in physical systems. Because if you take a physical system, let's say like a network of coupled oscillators, this system over time will always like to minimize its energy and find the ground state. And so you can see that there is there's an equivalence between the minimization of energy, if you will, on the physical system side, and the minimization of this objective function. And so the sort of the basic principle that we will use for this sort of physics-inspired approach is that if we can design a system whose energy function is such that its minima is exactly equivalent to the optimal solution or the minimum point of that objective function, then in that case, as the system sort of evolves through the phase space to find its ground state or lowest energy configuration, that in turn would then allow us to directly solve the problem at hand that we want to solve. And so that's really what lies at the crux of the sort of physics-inspired approach that we've been looking at. Now, of course, I want to sort of qualify this with the reality that the principle in itself might be elegant, and it's very interesting as a physics principle, but when you go on to really implement these systems, you have to worry about the more engineering-centric considerations, such as scalability, energy, power, performance, solution quality, compatibility with existing technology, and so on and so forth. And so these eventually become really important and can be the deciding factors in sort of the adoptability or adoption chances of a technology like this. That will be something that I will touch base upon in this as well. Now, of course, this idea of using physics to compute is not new in itself, and in fact, there have been multiple groups, multiple efforts that have tried to make this a reality using multiple platforms. So, for example, the most common one is that of the quantum annealers from D-Wave Systems in Canada, where they've been trying to build these quantum annealing processors that are based on this principle of energy minimization, and they are addressing problems in combinatorial optimization. So that's one. Similarly, there have been efforts in the optical domain with these coherentizing machines that use these optical oscillators and then networks of optical oscillators to really solve these problems in the COP problems. And similarly, the more classical one is the one that we focus on here in our group, which is that with charge-based or simple microelectronic-based oscillators. And so that is something that I'll focus on in this talk for today. So what I want to do with this slide here is to just give you a little bit more concrete example of how this equivalence between the combinatorial problem that is being solved. I mean, how the equivalence between the combinatorial problem that needs to be solved and that of the physical system can be established. And so, again, we'll take this example of the maximum cut. It's relatively easy to understand, and we'll try and establish its equivalence with a network of coupled oscillators under certain special conditions, like the second harmonic injection. And so I'll get to that in just a minute. But if you think about the max cut problem, we can essentially define it in the form of this equation that is shown here. And it turns out that if you like physics, this will seem very similar to the Ising-Hamiltonian that is used for, say, spin systems. And so, just to establish how this equation comes about for this max cut problem, what you can think about is that the max cut problem creates these two sets, and the idea is to assign the nodes to each set such that the number of nodes are the number of edges that are intersecting this cut is maximized. And so, what we'll do is we'll essentially assign a value of +1 to the set, and a value of -1 to this set. And what that really means is that when a node is assigned to this particular set, it gets assigned a value of +1. And if it's assigned to this particular set, it gets assigned a value of -1. And so what ends up happening is that the edges between these nodes are given by the product of the values assigned to each set. And so, for example, if I look at a edge that lies between 1 and 2, then the value assigned to that edge would be product of these two nodes, which would be -1 times +1, and so this edge will get assigned a value of -1. And what you can also show is that every edge that lies between the two sets, or the one that intersects this partition, will always get assigned a value of -1, because on one side of the edge, the node lies in the +1 set, whereas on the other side, it lies in the -1 edge. On the other hand, if you look at all the edges that lie within a particular set itself, so they don't essentially cross over, you can show that the value that will be assigned to this particular edge would be +1, because 1 times 1. And similarly, for an edge that lies in this set, it'll be -1 times -1, which will be +1. And so what you realize is that with this sort of assignment scheme, you can show that the edges that cross between the two sets are given by -1s, and the edges that cross that always lie within the set are given by +1. And so what you can then define this out as is that you want to minimize the total value of this Hamiltonian, because you want to then maximize the number of edges with -1 as the assignment. And so this whole sort of assignment can be quantified using this Ising-Hamiltonian here given by Jij, sigma I, sigma j. So sigma I will refer to a node value which would either be -1 or 1, and then Jij would essentially look at the connectivity matrix, or the adjacency matrix more specifically for the graph. So Jij equals -1 for if there is an edge between two nodes, and if it's 0, then Jij is equal to 0. And so you can essentially define the max cut problem as finding assignment for these sigma values, or the spins, such that H is as minimum as possible, or it's completely minimized. And so that's sort of the Ising-Hamiltonian that describes the max cut problem. But on the other hand, if you now look at the physical system here, which in this case is a coupled oscillator, and we're going to create a topological equivalence between the two, meaning that every node in the graph is represented by an oscillator, and every edge will be represented by a coupling element. And what you can then show, and I'm not going to go through how this equation is derived, but you can, it's not very difficult to do that. But once you derive this equation, you can show that this equation has very similar behavior to what we described for this graph here as well. And so here, instead of the two sets, we will define the two sets in terms of phases. So this 0-degree phase would be set 1, and 180-degree phase would be set 2. And what you can show is that when the nodes, or when the edges, the nodes that contain the edge lie in the opposite sets, then the phase difference equals +180 or -180, depending either way, however you define it. And that when that happens, this phi I minus phi j term goes to 180, and that the cost of that is always equal to -1, right? And so what that will mean is that when the nodes are in opposite sets, the energy is minimized because that contributes to a -1. On the other hand, when the nodes always lie in the same set, so be it 180 or 0, this term always goes to 0, and the cost of that equals +1, and therefore that increases the energy. And so the way to think about this is that this energy function captures the same behavior as this Hamiltonian that's shown here, and that in turn will as it tends to, as the system tries to minimize this energy function to get to the ground state by placing the nodes in the right sets, it will automatically calculate the solution to the Ising Hamiltonian. And that's the underlying idea. Now, of course, there are certain details that I have glossed over in the interest of brevity, but the general principle is hopefully clear through this slide. So the next thing that we did was we wanted to obviously validate this idea, and so we essentially set out to build this oscillator system on an actual integrated circuit. And we started off with a system of 30 relaxation oscillators shown here. So these are done using Schmidt trigger-based designs. And of course, the next thing that we have to worry about from the implementation standpoint is the coupling elements between the oscillators. And so this was done using a combination of transmission gates, which make them programmable, so you can turn on and turn off the coupling elements. And the capacitive coupling was used in our case. And so what you realize is that for a 30 oscillator system, it takes about 870 coupling elements to actually get the full programmable oscillator Ising machine, as it's usually called. And more importantly, if you look at the diphoto of this chip, you can see that the area occupied by the oscillator is the small square here, whereas the coupling elements occupy pretty much the majority of the area on that side. And it will turn out that this becomes a major challenge for implementing these machines overall. And it's an important factor that has to be optimized for moving towards practical solutions. Now, again, this is some quick experimental data that is measured actually from the chip. So this is the illustrative graph that I've shown here, and that this is the actual time domain waveforms. And so what you realize is that with this sort of computing paradigm, it's really the phases of these nodes that encode the actual information that we are interested in. And so here in this case, you can see that these two phases lie in the same sort of bunch, and then these are the other ones. So when you then plot it out on a phase plot, you can use this phase information to go back and calculate the max cut, which in this case is 8. And so, we know it's the optimal cut for the simple graph. And so at least it validates the operating principle of the system. Of course, we've done this for a bunch of other graphs across various node sizes and connectivity. And at least for these sort of smaller systems, which are like 30 nodes in our case, we do find that the solution quality is really good. In most cases, we find optimal solutions, whereas if not optimal, they're very close to optimal. Now, the next version of this that we were interested in is to look at the scalability of the approach. 30 oscillators is a good experiment, but again, it's not very competitive when it comes to solving real graphs. And so this is sort of the second iteration of our effort, where we went from a 30 node system to a 600 oscillator system. And of course, what the point I brought up earlier about the scalability of the coupling network, that really comes to the forefront here. So if you think about a 600 oscillator system, the coupling elements required scale as a square of the number of nodes. And so, for a 600 oscillator system, it's just impossible to get all those elements on the chip while being within reasonable limits for parasitics and so on and so forth. And so in this specific case, what we did was we essentially adopted this tile-like architecture. So the way we do this is we essentially define this single tile, which consists of 16 oscillators with all-to-all connectivity. And then each tile is then coupled to 6 other adjacent tiles to the in the network. And so that connectivity is also all-to-all programmable, but it's obviously only connected to the adjacent tile, because if you have to do global connections, that becomes really challenging in terms of the area requirements for this design. And so that's sort of the trade-off that you have to worry about. But this is just a summary of what's available on the chip. So we have 600 oscillators, about 29,000 odd coupling elements. The maximum degree that a graph can take is about 111. And then, some details about the readout interface, which allows us, we had parallel and serial readout on this IC. Now, again, I want to also re-emphasize the point about the area requirements. And so when we sort of break down the area for individual components, you can see that the oscillators are taking only about 3% of the area, and majority of it is consumed by the coupling elements, plus the routing that's required, implementing the coupling scheme, if you will. And so that really comes to the forefront, even while ensuring that we don't have a fully programmable graph. And so that's something that continues to be a challenge. And so if you're interested in working in this area and you have an innovative solution for this, please reach out. So this is the same part, but a slightly more sort of formal description of how the area affects. And the way we do this is think about it this way: that imagine I have a system of so many nodes, and I have a certain number of coupling elements at my disposal. You can see that even if you had a 600 node graph and say 100,000 coupling elements, you're only going to get a maximum connectivity of about 30% in the whole graph, and that's how severe this problem is. And so going forward, the more practical solution is to really look at sparsification strategies. How do you sparsify the graph? And of course, there's no free lunch there, in the sense that as soon as you start sparsifying the graph, you have to go back to some graph pre-processing that's required, things like graph embedding and so on and so forth. And so that's, again, something that we've been looking at. The other solution out there is potentially looking at emerging devices. So what you realize is that some of the functional properties that are required for these for implementing these systems, there could be other material systems, devices that might be better suited, or that have the potential to simplify some of the requirements that I've listed out here. But again, these are areas that are under active investigation, and so work continues to be done in this area. Another important point that I also want to emphasize is this idea of local minima. So it turns out that what this system is really doing when it comes down to minimizing its energy is that it's trying to find a ground state configuration that has the minimum energy. But it turns out that the phase space, or this high-dimensional phase space that it's trying to minimize, it turns out that it also has local minima. The system can get trapped in these local minima, and that, it turns out, can be that in turn, what it means from the computational standpoint is that it degrades the solution quality. And so you can see that in this specific example here, where for a 20 node graph, the system is easily able to find the optimal solution within the first, say, 45 or 48 cycles. But that's not the case for larger graphs. So in this case, we would have to wait for a long time for it to escape those local minima. So you have to engineer the noise. Annealing has to be engineered for it to actually get to these points. So this, again, the solution quality is also another important factor that must be solved, or that must be optimized further for practical application of these systems. So I just want to give you overall view of some of the ongoing challenges that this area faces. These are some results from the 600 oscillator demonstration that we did. So here is, again, just an example of the UVA logo, which is, again, configured as a graph. So the way to think about it is that we designed a graph where the resulting solution would be the UVA logo. So the red pixels represent one set created by the max cut, and then the yellow ones represent the other set. And so when you start out with the initial condition that looks like this, where it's pretty much random, you can see that the graph eventually, the oscillator system is able to find its optimal solution eventually. Now, I will say that there is some sort of post-processing that is required with these larger graphs to overcome the solution quality challenge. And that's something that, again, is going to be it's something that has to be optimized going further. But this just shows a potential sort of alternate approach where you can see what we did in this benchmarking plot on the right-hand side here is that when you compare the digital algorithms, the digital heuristic, which in this case is the manifold optimization solver, what you see is that as you increase the graph size, going from 200, 400 to 600, the computing time shows a very sharp increase, right? And you know, we are very close to the optimal solution or the best known solutions for these kind of graphs with the digital heuristic. Right. On the other hand, if you look at this oscillator-only approach, and we're talking of larger graphs now, we can see that, you know, for the limited time we measure, the solution quality is you know, it's suboptimal, but it is very fast, right? It's significantly faster than the digital approach. And so what we did was we took this as a starting point. So the solution that we obtained from the solver was a starting point, and then we used some very simple local search heuristics. And that allowed us to improve the quality of the solution without really facing a huge time penalty. And so that's, you know, that's another potential direction that might be interesting, where we have a hybrid approach that combines the best of both worlds, if you will, where the analog system really converges to you know, a really good guess, if you will, in a very short time frame, and then you can have the digital algorithm take it over from there to get to a very high, to a relatively high solution quality. As I mentioned that, you know, everything earlier was done with CMOS, but there's also some opportunities to look at emerging technologies. And so, for example, you know, the coupling network that I mentioned earlier that was implemented using CMOS and really took a majority of the bulk of the area on the die. You know, there are other technologies that are on the horizon that might be also suited for implementing these sort of architectures. And so here's an example of a case where we've also been looking at these ferroelectric transistors that we get access from global foundries. And it turns out that the interesting thing about these ferroelectric transistors is that they have this non-volatile threshold voltage. So you can set the threshold voltage of these transistors, and then that allows you to turn the transistor on and off in a controllable fashion in a non-volatile way. And so that so we've been evaluating that as a way to set the weights or the, you know, the connectivity of the graph. And we have some early interesting results which show that this might give us significant savings in the area as compared to the CMOS-based designs. But again, this is work under progress, and you know, we not only have to look at other challenges of emerging technologies such as endurance and variability, but this is a promising direction overall in terms of forward. Now, this is another application that we've just recently started looking at, so I don't have a lot of data on this, but you know, in the earlier cases, right, with combinatorial optimization, we were primarily trying to look at searching for the ground state, right, and that would then give us the solution to the COP that we were solving. But recently, we've also started looking at the application of this paradigm in sampling. And so this is an example of Gibbs sampling that was done with the OIM. And you can see that, I mean, this is the actual distribution. So this is a small network, so we can actually calculate the overall distribution and the probability of each state. But we can see that when we try and estimate that, which would have to be the case for larger problems, you can see that it's able to capture the probability distribution quite well. Even some states on the tails still have to be improved, and that's why it's still work under progress. And again, we've started to do this for larger graphs. So this is graph from the G set, which is 800 nodes and about approximately 20,000 edges. And at least our early results show promising potential. But we continue to work on this going forward. So the point I want to again emphasize here, though, is that it's another application would be looking at sampling, which is frequently used in training AI models, for example. Now we'll switch gears a little bit, but I'll quickly sort of mention this idea. So if you think about analog systems, right? It turns out that we we have to come up with a sort of framework for how for the design rules of such systems. So how do you design such systems, right? I mean, in the earlier slides, I really didn't give you a lot of information on what are the impact of parameters and so on and so forth. So, for example, in this case, you can consider K and Ks as like the hyperparameters, if you will. And what are the what is the guidance for designing them, or how do you optimize the values of these parameters? And it turns out that the approach that we have been looking at to answer this question, if you will, is borrowed from that of nonlinear dynamics. So if you think about oscillators or networks of oscillators, I mean, it's a classical a nonlinear dynamical system. And there has been a lot of work in the control theory domain of electrical engineering that has been looking at how do you analyze dynamical systems, how do you analyze nonlinear systems. And so recently we have started working on sort of developing the framework for analyzing and sort of coming up with the design rules, if you will, for these kind of oscillator-based networks. I won't go into many of the details in the interest of time, but again, the traditional ways is if you want to analyze linear stability, you can look at Lyapunov coefficients, which then give us very important insight into how various states are stabilized, how to destabilize certain states. So one example I can give you for that is, if you think about designing this oscillator Ising machine, from a control standpoint, what you want to do is you want to make sure that your ground state, which is this lowest energy given by this Hamiltonian here, is stabilized, whereas all other states are destabilized, because you don't want the system to get trapped in those local minimas that I mentioned earlier. And so it turns out that what determines the stability of a local minima, and of course this is looking at linear stability, is the Lyapunov coefficients. And so what you see here as the lambda L is the largest Lyapunov coefficient for a particular fixed point in the system. And so what you would like to have your parameters do. So here what we do is we really are changing the Ks, which reflects the strength of the second harmonic injection. And what we're trying to do is we want to come up with the right value of Ks such that the local minimas are all destabilized, whereas the global minimas are always stabilized. And so you can see that when, let me go from right to left, that'll make it easier. When I go from where I have very high Ks, it turns out that many of these local minima are stabilized, right? And so that increases the system getting trapped in the local minimas. Whereas on the other hand, if I sort of get to this intermediate value, you can see that only a few of the global minima are satisfied, and most of the local minima are unstable. So the system can easily escape out of those local minimas. And so your chance of finding the optimal solution is much higher with this configuration. And of course, if you reduce your Ks to such a low value that no particular state is stable, then you don't have an Ising machine. And you can see that in this graph panel at the bottom, where you can see the clear phase binarization. So it's either pi or 2 pi that you see here. Whereas in this case, the phases don't binarize and you don't really have an Ising machine. And of course, as I was telling you about the quality of the solution, you see that in this case, so the system never settles or is never able to find the optimal solution. And it always sort of gets trapped in these suboptimal configurations. Whereas on the other hand, when you have the right Ks, if you will, you can see that it's able to find the optimal solution in a majority of the cases. Out of 50 runs, we were able to get like 27 to be at the optimal value. And so, again, this is some snippets from this line of work that we've been looking at. And so we want to build bridges between control theory and computation with these dynamical systems. So I believe I'm going to have another 10 minutes. So I'll quickly cover another topic here, which is everything that we discussed until now was related to this Max-Scott problem. And so what ends up happening is, if you think about the Ising Hamiltonian and the properties of that Ising Hamiltonian, right? We essentially are looking at a specific class of problems and properties that we have exploited in that solution. And so the way to think about it is that for the max cut, we said that every spin can only take two values. So it's either +1 or -1, which means it's a binary system. And the other thing was the nature of interaction among the spin was always quadratic, meaning that it was only it was always pairwise. So sigma I, sigma j. And so that again has been sort of the workhorse of this physics-based computing approach, and there's been extensive amount of investigation that has gone on into that. But it turns out that many of the combinatorial problems, so even if you think about something like graph coloring or traveling salesman, do not actually fit that form very well. And so what happens in many of the cases is that you have to really take a problem and convert it into a form that will be compatible with this Ising solver or max cut, and then go on to map that onto the hardware and solve it on the hardware. And so that's sort of been the traditional approach of doing this. So the idea is called graph decomposition. But it turns out that that process of graph decomposition itself is not very trivial, and it can have a huge computational overhead in many cases. And the most sort of significant one being that the size of the problem that needs to be mapped onto the hardware is usually much bigger than the original problem itself. So for example, if I'm starting out with a 100-node problem, I might have to actually decompose that graph into a larger graph that is compatible with this Ising machine. And so I might have to end up solving a 150-node problem, for example. And so it turns out that there are those kind of challenges that come together. And so the way we approached this problem really was to ask the question: can we design systems with more dynamics? Right? Can we just improve the functional properties of the system itself? And so one of the things we have been doing is to formulate dynamical systems, come up with a theoretical description, and then subsequently implement them on hardware, where we no longer limit ourselves to only 2 spins. So now we have cases where the spin can take 3 values or 4 values and so on and so forth. And moreover, we also are able to formulate systems where the order of the interaction is no longer limited to 2 or quadratic. We can go to higher order interactions. So you can go sigma I, sigma j, sigma k, and so on and so forth. And so I like to think about this as a matrix where primary focus has been on the sort of the top left quadrant. But we are now beginning to design systems that will be able to address the other 3 quadrants as well. And the immediate advantage of that would be that if all these problems would be directly now mappable to the underlying dynamical system as well. And so that's sort of the underlying motivation behind this thrust of work that's going on. Now, in the interest of time, I'll sort of skip over these. I mean, I'll go a little fast over these slides, but if you have any questions, feel free to stop me. And so I want to just spend this talk about how we go about designing this this overall. I mean, how do we go about designing these other systems that can cater to the other 3 quadrants that I mentioned in the previous slide? And one approach that's usually helpful, and at least the way I like to think about it, is you always, when it comes to energy-based computing, if you will, it's always advantageous, in my opinion, to think about it in terms of rewards and penalties. So what you want to do is you want to make sure that certain configurations of the system are favorable, and the way to make them favorable is to define, you define an energy function that rewards the system in terms of lower energy by if it accepts those configurations, and you can also add a penalty for unfavorable configuration. So in this specific case, the way to think about it is that every time the system places the nodes on the 2 opposite sides, the system energy reduces. So that's a favorable configuration. But on the other hand, if let's say if the system places the edge on this set, say the 180-degree set, only, then that would be unfavorable configuration. Similarly, for this, if it places the edge only in the 0-degree configuration. And so these equations actually capture that behavior very well. And so what we did was we really took this concept to a 3-node system where instead of a 0, 180, we are now able to divide the phases into 3 parts, 0, 120, and 240. And we use the same idea where depending on what we want to achieve, we make sure that the right configurations are awarded. with lowering of energy, and the unfavorable configurations are penalized with increasing energy as well. Again, I'm not going to go into the actual math in the interest of time, but that's the general approach that we've used overall. And again, it requires us to define some mathematical functions, so on and so forth. And we've done this for 3-4 nodes, if you will. And these are some results that show our actual ability to solve graphs using these models that we've developed. So here you can see that this is the max 2 cut, which is usually the problem that I described earlier, where I'm dividing the nodes into 2 sets. But on the other hand, I can also do, with the new formulations, we can divide it into 3 sets, 4 sets, and so on and so forth. And so what that does is say, for example, if you're checking if a graph is 3 colorable, then you can directly use this model, this dynamical system, for doing that, instead of converting the graph into this and then sort of doing it with after the graph decomposition. And so those are some of the advantages that will come our way by formulating the system. Again, there are other, these are just examples of some of the problems that we've solved using this approach. So one of the hard problems that's very well known is that of integer factorization. So if I give you a number, how do I find the integer factors? And it turns out that that's another example of an NP-hard problem that can be solved using this dynamical approach. Another one is that of graph isomorphism. So how do you check if 2 graphs are equivalent to each other? And so that's another thing that we've built models for. And again, a bunch of other problems that we do have dynamical system formulations. Another part of the story in this case is here, in the earlier case, I only talked about going from 2-state to 3-state, but the order of interaction was always, quadratic. So sigma I, sigma j. But there's also interest in looking at what happens when the order of interaction itself is greater than 2, right? So what happens if I have sigma 1, sigma 2, sigma 3, sigma 4 that appears in the energy term. And so the way to think about that is the data structure that describes it is go from graphs, which are sort of these 2 edges, to hypergraphs, where edge can consist of more than 2 nodes that it connects. And the motivation for doing this, again, is that if we can formulate systems for this, then it would automatically allow us to solve problems like Boolean satisfiability, versions of Boolean satisfiability, and so forth. And that's something that we have done, that we've designed these systems for. Again, I don't intend to go through the math here in the interest of time, but these are some very simple illustrative results showing that these models actually work for solving these problems. Again, more data for the 4th quadrant, if you will. Finally, I just want to make a quick note here, which is what I described earlier was really focused on the actual physical implementation and having the system actually do the computation, meaning the physics actually does the computation. Another direction that we've been evaluating of late is that the question we're asking is, can we use these dynamical system inspired models? So at the end of the day, these are equations that are that describe the oscillator network. And what happens if we run them on an FPGA or a very dedicated accelerator and see how that helps? And here are some very preliminary results that show how this approach sort of show how this approach evaluates with some of the existing methods that are out there. And again, there is promise to this method as well, and we continue to evaluate it as we go forward. So again, some benchmarking between the 2 approaches. I don't intend to spend too much time on this, but I want to essentially conclude with this final slide here, just to summarize some of the key challenges and what would be a great target for these systems to achieve. And so if you look at the left-hand side, again, these are things that I mentioned during the course of this talk, where one of the key challenges that remains for this approach is the scalability of the physical implementation. How do you actually implement so much coupling? What are the overheads associated with that? If you want to sparsify the graph, then what is the pre-processing overhead that comes along with it? On the other hand, solution quality is how do you sort of come up with a principled approach to address the solution quality question in these sort of physics-based systems? So again, it's an interesting question that we're very, I mean, at least I'm very interested in looking at. And then finally, of course, the other part of it is also the reconfigurability, right? So right now, we have focused on designing these specific systems for specific problems. But can I create a reconfigurable platform that can be tailored, whose dynamics can be tailored for solving multiple classes of problems? And so the matrix that I showed you is sort of the first step towards that direction. And then finally, again, I mean, the way I see sort of the end target for a paradigm like this is, if you look at, you can get a lot of inspiration from the digital world itself, which is if you look at what has really worked in favor of digital computing, is you can see that the energy efficiency of digital hardware has essentially increased exponentially over time. So just like the Moore's law, where the number of transistors double every 18 months or so, depending on which time frame you're looking at, the energy efficiency has also doubled, and in fact that's termed as the Kuhm's law. And so the way I think about it is, unless one of the keys to success of a paradigm like this would be to identify sort of a way to keep increasing the energy efficiency of these computing paradigms, and if we can create the exponential trend, they might really have a chance. So with that, I'm going to end here. Again, I want to thank the students and the collaborators who've really done the work, and of course the sponsors who allow us to continue working on interesting problems. With that, thank you very much for your attention.
Thank you, Nikhil. So this is a very, very interesting talk. And actually, I have a couple of questions I want to ask. But so first, any questions from the audience? You can either unmute yourself or input your questions in the chat box. And maybe I think I can start first. Yeah. Sure. So first, thank you so much. So this is a really very inspiring talk and work there. And so first, please correct me if I'm wrong. So I think the computing system, that this is the physics-inspired computing system you described, is essentially still kind of the analog computing platform.
It is very much analog.
Yeah. Okay. Yeah, but we know that. So like for the OIM, there's also kind of the digital version, right? Like.
So I don't know what you mean by digital. So if you're so let me put it this way: if you're thinking about let's say using a two-state ring oscillator, right? That yes, the oscillator will only go between these two states. But what you can actually show, or what you will have to do, is that the dynamics, how the system searches the phase space, that is still very much analog. So at the end of the day, whether the next state, so maybe I can quickly go to that part. Let me pull up those equations here. Yeah. So again, if you think about it, right, let's look at this d phi I by dt equation, right? And so this is really what governs the dynamics of how the system evolves through the phase space, right? And so what would happen is, if you were to use, say, a ring oscillator, these functions would have to reflect the switching of the ring oscillator itself, right? But you can see that this equation fundamentally is analog.
Yeah.
Right. And so the form of the equation might change, but the computing is still very much in the analog to me.
Okay. And then a follow-up question is that, so because in the last part of the slides, you mentioned that, so they right now they're kind of the simulators, like using GPU, or right now you proposed the FPGA. So then, so I was curious about that. So how do you like to, especially like in FPGA, how do you kind of emulate this kind of analog computing?
Right. So yeah, again, I don't have time towards the end, but what we are essentially doing, Bo, is we are just taking the system of equations, right? We are exploiting the inherent parallelism in the FPGA in our case, right? And what we are trying to do is we are just trying to solve this, accelerate the solution to this equation, right? So that's very much digital.
So for example, like this, the sine, cosine, then you need like use the codic to like to
Exactly what it
discount.
is. That is
Oh,
right.
okay, I see.
That is right. So we have to use the chordic functions, for example. And I think there is a little bit of, I mean, so that's not per se my area of expertise, but some of the collaborators that I have on the list, I mean, they look at how to optimize the FPGA implementation, if you will, for just solving these, I mean, exactly how do I map the sine and the cosine function efficiently on an FPGA? These are the questions that they are very much interested in answering.
Okay, and in that case, because I know that actually one of the important part of work is that you investigate the efficient computing model, right? So such computing model actually it doesn't kind of depend on whether the underlying platform is the digital or the analog, right? For example, for these equations, this just kind of mathematical representations. And in that case, I was wondering so whether like using the FPGA or the digital ASIC design to implement such kind of the equations, maybe another kind of the alternative approach?
Yeah, so let me start out by saying that the jury is still out on what the best method is, right? So I do not know if there is a definitive answer to this approach wins over that. I think, and the reason for that would be, in my opinion, it turns out that it will eventually depend on the application that you want to go after, right? So, for example, if let's say if you're looking at, I mean, I'm just thinking of a hypothetical scenario where if you had very energy constrained resources, like there's very little, energy that you could use, and you were, let's say, okay with a reasonable solution, but not maybe the most optimal one with a lot of accuracy to it, right? In that case, maybe the analog alone might be good enough, right? So if, let's say if you're satisfied with a 90% solution quality, I mean, with some statistical guarantees, and you have to operate under energy extremely, let's say without cloud connectivity or anything of that sort, then it might be the case. But on the other hand, if you're looking at, say, a different case where you really, you couldn't compromise too much on the solution quality, and energy was not such a big issue, then maybe the FPGAs would be a better option, or some other, platforms would be better off. So that's the way I see sort of the scene play out, in the sense that eventually what turns out to be the best option will depend on what your end goal is.
Okay, I see. Yeah, because in my current understanding, I think most of the current exploration along this direction is the kind of the more kind of the analog computing based solution, right? Using the optical or using the analog CMOS device or the emergent device, something like that. Yeah.
Correct.
Yeah.
Correct.
But what I thought about that, I think that is also happens for other kind of analog computing technique, like those the in-memory computing. So was that when we consider about the scalability, that is also you mentioned in your in your in your slides that so analog that is kind of the inherent kind of the problem to solve the scalability challenge. I'm not sure whether the digital solutions or kind of hybrid solutions can kind of mitigate this challenge or not.
So yeah, I mean, let me put it this way, right? There are a whole bunch of unanswered but interesting questions, and that's what makes it interesting, in my opinion. So if yeah, I mean, if we knew everything, we wouldn't be talking about this. So I mean, everything that you bring up is a very valid one. I mean, I will say, for example, right, one thing you can rule out with this approach is that if you were thinking about, say, competing with a server farm on solving these problems, right? I mean, there is no point in trying, because they're going to win out any day. Where if you don't care about energy, if you're willing to throw as much resource at it as possible, then probably this is not the this is the way to go. But if that is not the case, then interesting options open up.
Okay. So we talk about the energy, and then another important metric is about the latency.
Exactly.
Yeah. So let's talk about if, for example, if I do not consider about the energy, but I care about the latency. So in that case, so whether this kind of computing model is still kind of the preferred choice or not?
So latency wise, again, I mean, so the short answer is yes. If latency is not too much of an issue here, because what we have seen and is that the system settles to, I mean, say 80-85% quality solutions very fast. However, having said that, right, it depends on what your quality, solution quality expectation. So if you, let's say, want a, solution that is, statistically going to go between 99.99%, I mean, then the latency might be a very big issue. But to be very honest, that is equally an issue for digital heuristic algorithms as well. I mean, for example, to give you one simple example, I think I have some.
Okay.
Yeah. So if you think about this, so what we did here was a very simplistic experiment, right? Where we just took Monte Carlo samples and, we tried to figure out the distribution of states in this particular graph, right? This is a standard G1 graph from the GSET data set. And what you realize is that even after, I think, 100,000 samples, and I know my student has already looked at like 2 million samples, we never find the ground state, right? Even for 800 node graph, you do whatever you want, you cannot find the ground state. And in fact, on the other hand, you can see that with the OIM approach, we are going to much lower energies that we can identify. Now, I don't know if this is the correct distribution or not, but we're already, getting to very low energies, right? And so it's not that the digital problem doesn't suffer from this, but the question really is, what is the relative degree, right? I mean, which one is likely to get you to a more lower quality solution? And I actually think the answer to that might be, the analog approaches. So digital approaches, I mean, so I think the way I think about it is where complexity really comes to, let's say, haunt you, if you will, is that when you want to go from the 95% solution to the, like 99.99 to 100%, I mean, that's when it really begins to affect, I mean, that's when the hardness of the problem really comes to the forefront.
Okay. Thank you. Thank you so much for explanation. And another very kind of the rough sort of the questions I would like to ask when I listen to a presentation. So actually, so right now you use the analog computing, that is kind of we can use kind of the continuous method to solve a kind of discrete problem.
Mm-hmm.
So then I was wondering, like, whether your method can be further extended to solve the kind of the continuous optimization problem.
So the answer to that is, I mean, in principle, yes, right? But I mean, again, my intuitive thinking about that, and it's a question that I've thought about as well, is that what makes combinatorial optimization so tough? What really, in my opinion, makes it tough is you don't have the availability of gradients, right? Yeah. So because you don't have the possibility of taking gradients on the phase space, right? You don't know what your next step should be. And that's why what we are really trying to do, if you think about it, is we're taking this sort of discrete phase space and we're trying to fit a continuous time system whose phase space will have, whose phase space will have critical points that match the discrete phase space, right? And so, I mean, my intuitive thought about that is if I have a continuous optimization problem, I have the ability to take gradients, right? So then is that really that hard? Now, again, I will admit I am not an expert on continuous optimization. So if there are problems that are still hard in that domain, I would be very happy to look at it. But my intuitive feeling says that gradients are very powerful.
yeah, you're right. Yeah, as long as it's differentiable and then you can use GPU to solve that. Yeah,
that's right.
Okay, thank you so much. And any questions from the audience? Sorry, I occupy too many Q&A time to ask questions. Okay, I think okay. If no more other questions, then I would like to ask a final question. Yeah. So you already mentioned about several kind of exploring topics that can be solved using this computing platform, and I was wondering, I was wondering because in one of your slides you mentioned that the area, I think the majority contribution of the area is from the coupling network and also the routing, and so actually that kind of a little bit surprised me because your actually functional unit is actually for the oscillator is just kind of less than 10%, and
Yeah.
I was wondering so why this happens is because kind of the physical constraints, like what we have like the similar to the IC layout, like because you have some design rule, some to limit that you must have kind of the minimum space, something like that.
No, so the way I think about it is if so if I give you a 100 oscillator or a 100 node graph, right? The maximum number of edges that I need is 100 square, right? So the simple problem comes down to that as the size of the graph increases in terms of the number of nodes, the number of edges increases as a square of the number of nodes. And so, if you think about, let's say, a 600 oscillator graph, which is what we've done, you will see that it takes 36,000 edges, right? And so that's really where it's a numbers game where one of the trend is increasing as a square, using a square law, while the other one is increasing linearly. And that, I think, is where the fundamental problem lies, right? And of course, you're looking, so there are other things like, for example, in our capacitive structures, right? We have to make sure that the capacitance has to be within a range that allows us to couple and so on and so forth, meaning that, you cannot make it arbitrarily small or you cannot make it arbitrarily large. So those are factors that obviously play into this, but I think fundamentally it's the law of those, how graphs work, where essentially if I have n nodes, I need n square edges to create a complete graph, right? Now, of course, that in most practical applications, you may not even need a complete graph, but then again, that has to be, that means that the design has to be tailored for a particular application. Again, a lot of this, I would say, one of the things we haven't, I would say, focus too much on, and maybe that that's something that is an interesting question going forward, is we have tried to keep it as general as possible, as much as because that would make it more applicable. But let's say if you're thinking about certain networks where just the average degree is very small or whatever, of the graph, and then in that case it might just be easier to come up with more efficient designs than focusing on this sort of all-to-all coupled design. But I mean, my interest in has been fundamentally to first understand the properties of the systems, and then it's easier to design around the final objective, if you will. So that's been the overall goal up until now.
Yeah. Because I'm from the EDA community, so I believe that so actually there's a lot of kind of design automation problems that in your computing paradigm. For example, you have kind of very obvious like the potential research topic is about routing, right? So how to reduce the routing that so in your specific domain there. And,
I completely agree. I mean, and one of the things I've been very interested, and I hope it happens in the near future, is that, I mean, traditionally this paradigm has been very much in the physics communities and some presence in the electrical engineering side of things, but it's traditionally been physics, and I mean, looking at statistical sampling like Gibbs sampling, or there are other types of sampling like Pot sampling. These have traditionally been the domain of physics. Some recently, I mean, in the past 10 years, there's been some active interest in looking at systems that can use that principle for computing. So the D wave from quantum annealers was one such effort. This coherentizing machines is another thing, where we're traversing more and more into the sort of the engineering side of things. But what I really hope to see is that there is enormous scope to make things better or improve from here onwards by involving new communities. So I mean, research communities. So what I mean by that is, as you mentioned, right? If an EDA expert comes and looks at the design, I mean, they might find 10 things that could be improved, right?
Yeah.
Similarly, one of the things that we have already sort of working on is this idea of if you look at oscillator dynamics, right? Oscillator dynamics have been a traditional it's been a traditional problem in the domain of control theory, right? How do you control nonlinear elements, and how do you control networks of nonlinear elements? And so this, in fact, this very slide is working with the right folks in control theory. We were able to look at how stability matters to the performance of the system and so on and so forth. And so to your, in fact, just to broaden what you're saying, the more communities that can look at this problem and see opportunities there, I think it'll only stand to benefit the overall area, in my opinion.
Okay. So thank you so much for sharing your insight and vision along this direction.
Thank you, Bo. Thank you for inviting me again.
Okay, thank you so much. So if no more questions from the audience, so let's thank our speaker again. So thank you so much. This gives us a very inspiring talk. And okay, so look forward to your future great work.
Thank you, Bo. Thank you all. Thank you all. Bye.
Thank you. Also, thank everyone to attend our this week's seminar talk. So see you next week. Okay. Thank you, Nikhil. See you.